So say some stuff for them in Portuguese, then I'll come back and make your presentation in English, and then you can give your presentation. Bom, pessoal, tudo bom? Bom, a gente está no nosso último seminário, né? Hoje. Vou fazer daqui a pouco a apresentação do professor, mas só para avisar, não sei se todo mundo viu, a gente postou lá no Classroom um formulário para vocês avaliarem a disciplina. Eu vi que tem umas pessoas que já responderam, mas só para a gente ter uma ideia do que vocês já acharam dos seminários até o momento, tá? We are here with Professor Salvatore Daniele. He's a professor at the University Ca Foscari in Italy, in Venice. He got his chemistry degree in University of Padua, and then did his postdoc there too, and became an assistant researcher in University Ca Foscari in Venice in 83, and then an associated professor in full professor in 2005. He has visited as visiting researchers a lot of universities in UK, USA, India, Spain, and his research interests are focused on the following research objectives: investigation on electrode process of organic, inorganic, and organic metallic compounds, development of micro and nano electrodes, development and application of scanning electrochemical microscopy, electrodic investigation solution with excess and with low electrolyte and real matrices, sensor development and applications in environment and food analysis, voltammetric and second characterization of nanomaterials and biosynthesis metal nanoparticles. Study on performance of electrode materials to be employed in fuel cells and photocatalytic process. He's the author of more than 140 papers and the editorial board of Talanta, Electrochemistry Communication, the Open Electronic Journal of Electrochemistry. So thank you so much for Salvatore for accepting my invitation, and you may give your lecture now.
Okay. So thank you very much, Mayara. It's for me really a pleasure to be here this afternoon to give this lecture. And I am particularly happy because I told before Mayara, it was a long time we didn't meet. So it's a really pleasure for me to have this opportunity. I am sorry we cannot meet anymore in the present, but I hope in the future we can have the opportunity to meet in person again. So the topics of my talk are here summarized. It is concerned with the development of electrochemical methods and sensors for the detection of drugs, small molecules, and silver ions coming from silver nanoparticles. Actually, these are some of the topics we are investigating in the last few years. So I hope to give an overview of all these topics in this talk. But before starting with the talk, I would like to present briefly my university, Ca Foscari University of Venice, which was established on August in 1868 as a Royal Business College. Actually, for Italian university, it is not so old, but Ca Foscari University of Venice was the first educational institution in Italy to offer higher education in business and economics. In the more recent years, and nowadays, Ca Foscari offers 4 main subject areas of teaching and research: economics, humanities, languages, and sciences. This picture you see here is the main building, and it is located in the Grand Canal of Venice. Probably most of you know how Venice is made. This is an island. It's as fish shape as can be seen, is shown here. This is the Grand Canal, which starts more or less from the railway station and goes through San Marco Square, which is the most famous place in Venice. So most of the buildings of the university are located in the historical city, as you can be here from these red symbols. And up to about 5 years ago, also the scientific campus was in Venice. And it was located here, very close to the sea door port of Venice. And when Mayara came in my lab many years ago, she came here in this place. I can show you some picture of the buildings, and in particular some place where which are present in the main building, Ca Foscari University. So, for instance, this big hall is the place where the rector has his offices, and often it is used for some special events. This, if you see here, this is the main hall. It's called Cadolfin. It's the hall where usually people get the degree. It's a very old and very nice with the paintings hall. Typically, it's open just for big events. Otherwise, they don't. It is not open. It can be visited under appointment, because they restored recently all paintings in the hall. These buildings here, probably Mayara recognized them, were the building of the old scientific campus when we were here. It was a factory, actually. This building was a cotton factory, which was restored in more recent years. And here is one part of the internal part of the campus, the old campus. And this is the street where, if Mayara remember, we went to buy sandwich for lunch. So here there is the bakery where we went to buy sandwich.
I remember, sorry, I remember. I talked to everybody how great the sandwiches were.
Okay. So now we move it to the mainland in Mestre here. It's a little bit far away from the island. We have to cross the sea, the laguna, okay? And so this is a new campus. And here you can see, sorry. In the department belonging to the scientific area are two. The department of molecular science and nanosystem, at which I belong, and the department of environmental science, informatics, and statistics. We have first degree and second cycle degree programs. Eventually, if someone is interested in the second cycle degree program, you can have opportunity by visiting our website to choose some of them. So here are some pictures of the new campus. You can see very new buildings. This is the main tower where there are offices, the library, and the main hall where in Mestre we have big events or conferences. This is the the black tower is the place where there are lifts and other facilities. The rear part, this one, is the part where there are offices, and mine is, I'm talking from here at the moment. This is my office. I'm talking from here. These are other buildings in the campus. This is another picture. And now a new one is going to be built here in these spaces. These are pictures of the library, inside the library and outside the library, where we have a bar, some place where we can get food and other, and sandwich and so on. So now moving forward to the talk, I hope to be able to treat all these topics: development of cheap and easy-to-use electrochemical sensors, for electroanalytical methods for the detection of drugs for therapeutic drug monitoring, development of miniaturized membrane-free voltammetric and thermometric sensors for the detection of gaseous species based on the use of microelectrodes and room temperature ionic liquids. And in the last topic is the investigation of the stability of silver nanoparticles, either commercially available or produced by biological approach in aqueous solution and liquid food simulants. So all measurements concerning this aspect are carried out by dynamic electroanalytical techniques. I don't know if you are aware about the dynamic electroanalytical techniques, which means usually you record the current as a function of an applied potential in an electrochemical cell, as that's schematized here. Usually, we have a working electrode, which is the most important electrode, at which the process of interest occurs. Then we have a reference electrode, which is able to monitor exactly the potential of the working electrode. And then we have a counter electrode, which allows current to flow between the working and the counter electrode itself. The instrument which allows to measure exactly the potential against the reference electrode, and at the same time to monitor the current which flow between the working and the counter electrode, is called potentiostat. The responses one obtains from this kind of instrumentation depends on the potential waveforms applied at the working electrode. There are many, there are many waveforms. I missed one slide. There are many waveforms available, but we actually used just three, which is chronamperometry, linear sweep scan excited voltammetry, and the differential pulse voltammetry. There was, sorry, I lost it. There was one more slides concerning the waveform which can be applied to, which we applied for making this measurement. Anyway, I'll talk about them during the presentation. So as for the first topic, development of electrochemical methods and sensors for the detection of drugs, in particular, I had in plasma samples. This aspect is, this topic is within the so-called therapeutic drug monitoring practice. This is TDM. It's a practice which typically is used in hospital to monitor the concentration drug in patient body fluids in specific time intervals in order to verify whether the drug concentration is within a well-established therapeutic windows. What is a therapeutic windows? This is shown here. The therapeutic windows is the concentration within which the drug is effective and does not give side effect. It's not toxic, in other words. So once the drug is administered in the body of the patient, it follows with time a trend like that shown here. At the beginning, the concentration in the plasma increases in the body fluids in general, reach a maximum and then decreases. So in order to establish if the period in which the concentration is within these windows, one has to do many measurements. And this is the main problem, because a large number of samples need to be collected and analyzed. Typically, to do this kind of measurement in hospital, the techniques employed are the classical ones based on chromatography and mass spectrometry. SPLC coupled with mass spectroscopy, and so on, mass spectrometry, and so on. Or SPLC coupled with UV detector, and so on. These techniques are very have a high accuracy, sensitivity, and reliability. But unfortunately, they have a high cost, lack of portability, cannot be used closer to the patients and the bed at the bed patient, and also often require long time analysis. So for these reasons, recently people has tried to provide some other kind of techniques to be used much more easily, and which are rapid and so on. And electroanalytical techniques fall within this kind of technique. In fact, they possess high sensitivity, can allow fast analysis. The cost of the instrumentation is rather low. The instrumentation is compact, requires small amount of samples, and can be used, are useful for point care analysis. So having this kind of goal in mind, we started with, in collaboration with the Cancer Center close to Venice, developing some electrochemical methods. There are not so many electrochemical methods available for drug monitoring, or at least there are no really applicable, real and reliable methods for the detection of drugs in body fluids. There are many papers dealing with the detection of drugs, but most of them are not very useful and not directly applied. It cannot be directly applied for in real samples. So one of the drugs we started working with was Irinotecan. This is the formula of the drug. This is a very long name. Usually people call it by this acronym, CPT11. Irinotecan, it's actually a prodrug. It's not directly the drug which react with the cancer cells. And it is used mainly in colorectal cancer treatment. I say that it's a prodrug because the real drug is this compound here, which is produced from from CPT11. It is activated by an enzyme, which is the liver carboxylesterase, which produces this molecule. This is the real drug against cancer. But this cannot be administered directly because it's very, very toxic. So people usually administer this compound, which is much, much less toxic. Okay. Unfortunately, CPT11 provides a lot of metabolites. All these metabolites share with the CPT11 the same structure, same chemical structure, which means one has to expect some interferences in doing determination of the drug. Another aspect which must be considered that CPT11 is usually administered as CPT11HCl, which is the chlorhydrate form of this compound. Because this tertiary amine here can react with the HCl to provide a form which is more soluble in the injection form. So there are many issues related to the detection of CPT11. Apart from the number for the metabolites, there are other problems related to the therapeutics, which usually are administered together with the CPT11. However, in plasma, there are many endogenous compounds which can disturb interfere with during the analysis. Considering that the concentration of endogenous compounds like uric acid, ascorbic acid are present in the matrix at a high concentration level, while the therapeutic levels of CPT11 is of few micromolar or submicromolar levels. Another important aspect to be considered that the CPT11 is for the majority amount bound to protein plasma. Up to about 65% is bound to plasma protein, which means we have to denaturize the plasma samples in order to extract the entire amount of the CPT11. So all these aspects must be considered in trying to control and to make a reliable analytical methods for the detection of the drug. Of course, this also holds for electrochemical, when electrochemical approach are used. So we started to investigate, first of all, the so-called voltammetric behavior of CPT11. So voltammograms are responses like high current against potential. The signals, which are shown here, are related to the oxidation or reduction of moieties present in the molecule. After a screening of various solvents, which could be useful for making detection of this compound, we ended with this kind of solvent and this kind of mission, which means acetonitrile was the most useful solvent. For electrochemical measurement, we have to add a supporting electrolyte, and we realized that TBA-PF6, it's a good one, tetrabutylammonia S4-phosphate is the name. The working electrode which we can do measurement is simple. It's a glassy carbon, which is commercially available. So we used a reference electrode which was a silver wire in order to avoid any contamination with classical reference electrode. And a counter electrode was a platinum wire. So the various peaks here you see in the cathodic region and in the anodic region refer, as I told you, to different moieties of the molecule present here. But from our point of view, the most important part of the molecule which provides useful signal for the analysis of CPT11 was the tertiary amine of this part, okay, and unfortunately, which provide this peak here, but unfortunately, simultaneously, we get also a peak due to the oxidation of chloride ions. In the negative region, there are several peaks which could be, in principle, exploited for detection of CPT11. But as I'll show you in the next slide, most of these peaks here are provided also by the metabolites of CPT11. Moreover, for practical analysis, the cathodic region, from an electrochemical point of view, typically is not a good choice, because there are interferences also due to reduction of oxygen. Otherwise, we have to purge the solution with nitrogen or other inert gas. So when we explored and investigated the voltammetric behavior of all metabolites which can be produced from CPT11, and we examined the cathodic region, we could observe that almost all peaks present in CPT11 are also present in the other metabolites. Instead, in the anodic region, okay, it's almost free from other signals. So we choose the anodic region, and in fact, when we made cyclovoltammograms in mixtures containing CPT11 with other metabolites at same concentration level, while in the cathodic region we see a complete overlap of the signals, so we couldn't differentiate the various species. In the anodic region, this peak here, which is related to the oxidation of the tertiary amine of the CPT11, it's almost free from interferences due to the other metabolites. Cyclovoltammetry is not typically a technique which is used for quantitative analysis because it's not very sensitive. So in order to quantify at trace levels the compounds, differential pulse voltammetry is preferred. So we use a DPV, which provide responses like that, those shown here, are peak-shaped, bell-shaped, peak-shaped. And by using this technique, we could detect the CPT11 at the simple glassy carbon electrode with this kind of analytical characteristics. Limited detection was the linear range of the measurement varied between 0.5 micromolar to 8 micromolar. Sensitivity was quite good. Detection limit was 0.11 micromolar. Log quantification limit was 0.37 micromolar. Reproducibility, as shown here, is very, very good. But this measurement, this kind of results were obtained in synthetic media. So we had to face, as I told you before, with the other interferences due to the matrix and also co-therapeutics, which can affect, which can have an interfere with the measurement. So in order to get good results and reliable results, we have to make an extraction of the drug from plasma samples. So in order to do this, we employed some commercially available columns, some solid phase extraction columns, which are denoted with this acronym, Strata XL, provided from the Phenomenex. By several procedures, by treating the column before and then the sample with different kind of media and solvents, we are able to eliminate from the sample all interference. And consider that we employed for the analysis of irinotecan in plasma, spiked with the irinotecan at the beginning, only 125 microliter of plasma. This is important. So by using water ethanol mixtures, we could eliminate all interference, and while iron CPT11 remained trapped within the column. So the last step was the use of acetonitrile. For this reason, we employ acetonitrile in the previous measurement, which can extract almost completely the CPT11 from the irinotecan, from the plasma. So at the end, to perform measurement, electrochemical measurement, we have to add the supporting electrolyte and the other media in which were established before in the synthetic solution. And then we obtain, of course, the DPV without interferences. Of course, we made a recovery test to verify whether the procedure was reliable. And here are the data obtained in the recovery test, for instance. You can see, starting from 0.5 micromolar up to 6 micromolar, the recovery test provided value varying from about 19.4 95 to more a little bit more than 100%, which means that the recovery was very, very good. So to verify that this procedure was actually reliable for quantification of this drug, we performed measurement in samples, plasma samples, collected from patients affected by colorectal cancer, which were treated with CPT-11. So these are the responses we obtained, and the quantification was performed by the standard addition method. And then we compared the value obtained by DPV. These are the value obtained by DPV, with those obtained by the SPLC-MS method, which it is at the moment used in the hospital. And as you can see here, there is some differences, okay? Around 11 and 20% for these two samples. But anyway, they are still good, because considering the differences in the procedures and the technique employed. Anyway, the doctor considered these differences okay for TDM measurement, for TDM application. A similar investigation was conducted for the detection of imatinib in plasma sample. Imatinib, another drug which is used for chronic myeloid leukemia. In this case, the compound is still a molecule which is quite difficult to read completely, and it doesn't provide many differently from the other drug. It doesn't provide many metabolites. It provides just one metabolite, important metabolites, which are actually has same function act as imatinib. So it is considered. It is not considered as an interferent. Other metabolites actually are very affect very little the measurement. So the detection of this drug is much easier. The interferences may be due to the plasma endogenous compounds, as before I said for irinotecan, and also by the fact that imatinib is bound to plasma proteins up to about 98%. So it's strongly bound to plasma protein. In this case, in order to get good results, we changed a little bit either the techniques, the voltammetric techniques employed, but also the solvent. The best solvent that provided good results was, in this case, ethyl acetate in a solution containing strong acids, and again using glassy carbon electrode. In this case, we used for the investigation this waveform, which is a psych voltammetry with 3 segments. In this case, in the first stage, in the Nordic region, we got this peak here, which provides products which adsorb on the electrode surface. So this is the forward scan. When we go back, there is this peak here, and going back again with this segment, we got this peak here. So these 2 peaks are species which are adsorbed on the electrode surface. And these 2 peaks here provide a good way to detect this drug at low concentration levels. In order to increase the sensitivity with the technique I shown you before, we used a small variation of the technique, which is called adsorptive stripping voltammetry, which means before applying this waveform here, we apply the constant potential for a short time. The time was varied between about 10 to 30 seconds. So we started the potential from the scan from this potential here. We went this direction before, and then we went back to this direction. So you can see here the two peaks, peak 2 and peak 3, which are those we use it for the quantification. These are the equations we obtained from regression line, okay, which provide very, very low limit of detection, around 8.2 nanomolar, and log of about 27 nanomolar. The linear range was between 40 and 900 nanomolar for peak 2, and similar values, similar characteristics were obtained for peak 3. Again, in this case, also in this case, we have to deal with the interferences due to endogenous compounds, which cannot be eliminated directly from the plasma matrix unless one do some separation before the electrochemical measurement. So in this case, we use a different kind of column. A novum from Phenomenex were employed. These are also commercially available. The extraction procedure was quite easy, and we could detect the imatinib concentration starting from about 50 microliter of plasma, much less than before. It was the imatinib was completely extracted from the plasma sample using the ethyl acetate, the solvent, which then it is used for the electrochemical measurement. So in this case, it's much simpler, the procedure. Of course, once you get the liquid extract from with the ethyl acetate, you should add the supporting electrolyte, acid, and so on, in order to perform the electrochemical measurement. Again, in this case, it is shown the results that we obtained for peak 3. This is the amount of imatinib present in the plasma, and this were to a standard addition to obtain the concentration.
Salvatore,
yeah?
Sorry, I will have a question here from Camila. Do you mind if I do the question now? Can I? Camila is asking actually about the plasma sample, how you obtain it, because I don't know, you take the blood from the person and then separate it with the plasma. How you obtain the sample, the plasma sample?
You mean the one due to the patients affected by cancer, or the other samples? Because we used it before, probably I didn't say that. We used it at the beginning when we made this kind of experiments to verify if the procedure was okay. We used plasma samples collected by people who were not affected by cancer. We obtained this plasma sample from the hospital, from the cancer center. Okay, so we didn't treat it directly in our laboratory.
Okay, yeah, I thought so.
And of course, we also got the samples from patients which were affected by the cancer from the hospital.
Okay.
Consider that they cannot provide so much amount of samples. Okay, they are really they don't want to give too much sample around. For this reason, we have to collaborate with them.
Okay, but that's my doubt. The patient has to approve, give their sample to analysis.
Sorry?
If the patient has to approve his blood being analyzed by you, the plasma.
Yeah.
Yeah, okay. I have another question here from Guilherme. He's asking how the choice of the column is made in each case, because you used different columns, right, to make the...
Okay, this column here, this column are commercially available. The volume of this column is about 1 milliliter. It's filled with, actually we don't know exactly what there is inside, because this column are protected by patents. So we asked to the provider which kind of column was better. So we had to ask them.
Okay.
For this reason, we changed the columns. We proved the same columns for the two drugs, but the previous one didn't work for imatinib. It worked well with acetonitrile, while this column here, this novum, didn't work with acetonitrile. So for this reason, we have to change the column, which probably the material present inside provides specific reactions or phenomena, or with the drug, as I said before, for a CPT11, or with the species which interfere with the analysis. I mean, with the endogenous compound, ascorbic acid, uric acid, and so on. Okay. Anyway, these two columns and the procedure we developed were really good to recover from 90 to more about 100% of drugs. Okay. I must say that two procedures we made a patent on that. So the patent has been published about last year in the summer, when we after this kind of investigation.
Nice. I have one question, my question. I think it was the previous slide where you show the adsorbing strip voltammetry. You apply the potential and did the cyclic voltammetry after, not a...
You mean in the first part?
No, with this one we are doing the next one and one more. Yeah, this one.
This one.
Yes. So you did the preconcentration time, and then apply the cyclic voltammetry, not differential pulse voltammetry, for example, because you wanted both.
In fact, we applied this waveform here. Preconcentration at 1.1.
But why not use, for example, the differential pulse voltammetry?
We tested it.
Yeah.
Actually, it was you see here. This is really sensitive because we accumulate the oxidation product from here. So if you look at that, so here you get the oxidation product. The oxidation product doesn't go in the solution, but at the electrode surface. Okay. So if you accumulate the oxidation product here, you accumulate the product. And this is directly proportional to the amount of imatinib present in the meat. Okay, so actually we also tested the DPV in order to verify whether the sensitivity could be increased, but it didn't work much because I believe because the absorption processes are not good with DPV, because DPV tried to eliminate the background current due to capacitive current. Okay, but when you absorb a species on the electrode surface, somehow you increase the capacitive current. In fact, if you see here, the capacitive current is quite high. Okay, but anyway, the results were much less reproducible.
Okay, interesting.
We tested it, but it didn't work much. We tested also square wave voltammetry. It didn't work.
Very interesting. Thank you.
Welcome. Other questions?
Just let me check. No more questions so far.
Okay. So also in this case, okay, we made measurement with different patients. Okay, 3 patients in this case. And here are the results. This is the method employed for developed by us. This is the values obtained by SPLCMS. In this case, the reproducibility and the agreement between these 2 values were much better than the previous one. Okay. Tell me when I have to finish my talk, because now I would like to move to this other aspect, which is related to the detection of the drugs. Because the cell I showed you before, okay, this one, it's quite huge. It's not easy to use it to bring, for instance, in an hospital, to use close to the bed of the patient. So we try to develop a method to miniaturize the cell, or at least to use simple systems. And at the beginning, we tried to use commercially available screen printed electrodes, which are provided, for instance, from a company. But a problem with this kind of electrode is that the insulating part, the inks that are used for their production, was not stable in organic solvents, because this kind of electrode typically are used for aqueous solution, not for organic media. So in this case, my PhD, who spent a period in the laboratory of the electrochemical and analytic in Lausanne with Professor Giraud and one of his co-workers, tried to develop to test new inks to prepare screen printed electrodes. So they use this kind of inks. Okay, I just show here the acronym of these inks. Probably they can be found in the literature in internet by because I think the provider can allow to read this kind of acronyms. Anyway, using these machines, which was developed in this laboratory, able for large-scale production of the disposable electrodes and electrochemical cells, we try, by using this kind of inks, to construct a small cell like this one, And here is shown the materials with which these are composed. We have a silver reference electrode, a working electrode which is made by carbon nanotubes, and a counter electrode also made by carbon nanotubes, but have this electrode, the counter electrode, have a much bigger surface area. So we tested this electrode by prepared by these new inks before in using a normal probe, which is whose electrochemists know, ferrocene methanol, in order to test the stability of this electrode in organic solvents. We used, apart of the ethyl acetate acetonitrile, which were those of interest for us, but we used also the methyl sulfoxide emissions of water and methanol. So here are typical cyclovoltammograms we obtained for this probe here at different scan rate, okay? And we tested the stability with time. So as can be seen here, acetonitrile is the worst solvent even for these inks. The stability is rather low. 0.5 2 minutes is the maximum stability. And after that, the results are really strongly irreproducible. With ethyl acetate, the stability was much better, 10 minutes, which means we could make one measurement, or at least 1 or 2, 3 measurements of the type I've shown you for imatinib. We couldn't make measurement of irinotecan with because in acetonitrile, this electrode have very, very low stability. In the methyl sulfoxide and water methanol mixture, the stability is much better. They can be used even to make an entire calibration curve. So anyway, we tested these electrodes using ethyl acetate as a solvent for making the measurement of imatinib. Okay, and here are shown the CV, the voltammograms we obtained with this printed electrode. And this is the quantification, the peak tree, with which we made some quantification. These are experimental points. This is the repetition we made with the same electrode. We repeated the measurement 3 times with the same electrode. As you can see, although there is a straight line which can be drawn from this point, the reproducibility is very low. Probably this kind of electron can be used just for one measurement, and then you have to change the electrode to make the second and so on for the other measurement. But we actually did this kind of measurement, but probably the surface area of the working electrode was not so reproducible, and also in this case we didn't get good reproducibility. Anyway, by trying other inks, probably one can get some stable system also in some kinds of organic solvent. But by now, we didn't succeed to achieve these results. So sure, the other topics, tell me when I have to stop, because there are many slides.
Okay, I think you can continue talking, no worry.
Okay. Yeah, maybe I try to have
time, of course.
Sorry?
If you have the time, of course. I think
no, I have time, okay.
Okay, have like half an hour more.
the other topics is concerned with this amperometric-free amperometric sensor for gas analysis devices. What we try to do is to imitate the Clark type electrodes, okay, for gas analysis, but avoiding to use a membrane, because the membrane limits diffusion of the species from the atmosphere inside the solution. Okay, so the drawback of the Clark type electrode is that the response time is quite long. Okay, it required 90 seconds and so on. Electrolyte inside the medium hardly survives just in change in temperature. Okay, so we try to prepare miniaturized electrochemical cell for gas analysis by using room temperature ionic liquids, okay, as solvent, which can be applied directly on the electrodes, on 2 or 3 electrode systems. Why ionic liquids? Ionic liquids are very good properties. Have a wide electrochemical windows, has a high inherent conductivity, low volatility, high thermal stability, and also tunability by changing or the cation or the anion of the room temperature ionic liquids. So the design we proposed for this measurement was made by using a double barrel pipette, which was in which we placed 2 electrodes. One was a microelectrode of 25 micron diameter, a platinum microelectrode with 25 micrometer diameter, as can be seen here from a SM image. This is, and this electrode here was used as a working electrode. And then we put on the other side of this double barrel pipette, micropipette, a bigger electrode, 300 micron, which was used as a counter electrode. I can't say much about the theory of microelectrode, but when people use a microelectrode, a 2 electrode cell is enough to obtain good results, because the ohmic drop, the current measure are very low. So one does not need the 3 electrode systems. Okay, to make the contact between these 2 electrodes, a thin layer of room temperature liquid can be applied. And this room temperature ionic liquid can be applied just by deep coating. So the systems we realized is this one. This is a system which allows you to make measurement in gaseous atmosphere. Okay, so we tested this system for using different ionic liquids. Here there are some characteristics of the ionic liquids. And also, before starting with measurement in the gas phase, we want to verify which kind of responses we obtain in this media. So this is, for instance, the response we obtained by room temperature ionic liquid, this one in particular, which was loaded before with ferrocene. These are 2 responses obtained with 2 different ionic liquid with different thickness of the room temperature ionic liquid. So as soon as the diffusion layer within the ionic liquid is much less of the thickness of the ionic liquid film, the responses are almost not affected by the thickness. Okay, this means that you can make with this simple approach, deep coating, okay, a suitable film to obtain suitable responses. Then we moved, of course, to gaseous species, and the first species we explored was oxygen, of course, and these are typical responses obtained for the oxygen reduction in gas phase with the system. Okay, here it's the container in which we put our probe. Okay, I don't know if you can see the probe here. Anyway, it's inserted. This one was inserted in this container, and by this system we could provide the adequate mixture of oxygen with nitrogen. This is a sort of calibration plot we obtain by doing measurement with the probe using cycle voltammetry in different mixtures of oxygen and nitrogen. So by using the weight of this CV plotted against the percentage of oxygen in the measure, we obtain a very nice linear calibration plot. The reproducibility was within 4%, very good. Detection limited up down to 0.1% VV oxygen. So measurement can be performed quickly, much in a simple way by amperometry, by using chronoamperometry. In other words, by performing the potential step for a given amount of time. For with microelectrode, you can reach steady state in a short time. And again, the current, the limiting current in this case is proportional to the percentage of oxygen in the mixture. Okay, to test the suitability of this system, because these measurements were performed in under static conditions, which means we saturated the container with this mixture and then we made measurement. But the system works also under flow conditions. And these are the signal we obtain while varying in flow condition the percentage of oxygen in the mixtures. And again, the current, the limiting current against the concentration, here is not time, it's wrong here, it's percentage of oxygen, provide a good linear trend. To prove that this sensor can be used several times, we made several steps like those shown here, which means we obtain current against time profile in the absence of oxygen by sending a given amount, a constant amount of oxygen, keeping the oxygen atmosphere for a given time, then sending in the container nitrogen, so the current decreases, and so on for several times. As you can see, the reproducibility is very good. So you can use this system many times, which means you can monitor the oxygen concentration in simple way. And to verify that this was the case, we used this room temperature Ionic liquid microprobe for monitoring oxygen in air for several hours. Okay, here are the responses of oxygen obtained by fitting the current signal on a calibration plot. And the different point, apart from the reproducibility, the different point refer to measurement performed also with a system which provide another system, not with our probe, which controlled, which provided the amount of oxygen present in the mixture. So the reproducibility and the agreement between the series of data is very good. So the same probe could be used, for instance, by changing the room temperature ionic liquid for other gaseous species, for instance, for SO2. And this are a series of measurements performed in an atmosphere of SO2 created by developing from sodium sulfate SO2 and transferring it in the cell, in this container in which was put our microprobe. Okay, and as you can be see here, the limiting current of the responses increases with time, which means the higher is the concentration of SO2 in this container, the higher the peak current, the wave current, the limiting current of the wave. Another interesting measurement we made by changing again ionic liquids. In this case, we used the basic ionic liquids to measure, to detect aldehyde in headspace. In aldehyde in headspace are typically monitored by gas chromatography. So we want to see whether using this probe and this specific ionic liquid, we could provide measurement, a reliable measurement of aldehyde. Why we use a basic room temperature ionic liquid? Because from the literature, it was we observed that we have realized that basic ionic liquids are employed for condensation reaction involving aldehyde, which means catalyze somehow the aldehyde reactions. So we explored the possibility to use this probe for two aldehydes, propanol and hexanol. Hexanol in particular is very useful for food analysis. So this is the apparatus we use. So the probe is the same, this one, which was kept in the atmosphere of a vial, which was immersed in a water bath. This in order to check the temperature, because the volatility of aldehyde strongly depends on temperature. So these are the results we obtained for propanol, and this for hexanol. Of course, the volatility of the aldehyde depends on time. Here we placed just a drop of the two aldehydes. Of course, we repeated 2 times this experiment, once for propanol and the other for hexanol. So, and we got this kind of responses. At the beginning, the current increased and then reached the plateau, which means that the hexanol achieved its maximum concentration in the headspace. Similar results were obtained for hexanol, propanol, and hexanol provide similar results, but as can be seen here, hexanol provides much lower current with respect to propanol, which is in agreement with the vapor pressure of the two aldehydes, which are here reported. We check the effect of temperature. Okay, here are typical voltammograms obtained at different temperature. As the temperature increases, the amount of vapor increases and the current rate of the wave increases. For practical application, we try to measure the hexanal, which was developed from squalene samples, which were spiked with different amounts of hexanal. Squalene it's often used to simulate matrices, fat food, for instance, butter, or things, olive oil, and and so on. So here are typical responses we obtain in dead space of these squalene samples, which was placed in the bottom of a container. And this squalene were spiked with different amounts of hexanaldehyde. And as can be seen here, the current we obtained was proportional to the amount of to the ppm of hexanaldehyde present in the squalene. So we made this measurement at different temperature in order to verify whether the proportionality between not only with the concentration but also with the temperature. And these measurements were made by using either voltammetry, so we obtain waves like that, or amperometry, which provide current against time responses. Results were quite good with the two techniques. These are the detection limits obtained at the different temperature, either by voltammetry and amperometry. We made also, these are another examples in which we use chronamperometry, okay? And in this case, we tested another effect, the possibility to reuse this the same problem for many times, okay? Because the oxidation product of hexanal or propanal usually affect somehow the small thickness, the small amount of ionic liquids which is placed on the surface of the microprobe. So in order to get good results in this case, we have to apply a quite complex waveforms. It's like a pretreatment step. This form, each of these steps means that we apply a pretreatment of the electrode surface, and then we apply the potential path to obtain the current. So repeating this waveform continuously, we got this kind of responses. And each of these responses, the limiting current of each of these responses is proportional to the concentration of the aldehyde. Here, I think this measurement refers to hexanal. So in order to verify whether this measurement can be reliable, we apply the method developed for voltammetric sensing of the head space of hexanal chemical, which can be developed from edible oils. In particular, we used sunflower oil samples. When oils are kept for a long time in in not well-controlled zone, they are subject to decomposition. And one of the products which is formed is hexanal, which is a marker for oxidation of fat products, for fat food products. So we follow, under stressed condition, the development of the gaseous species from this sunflower oil sample. We follow this process for at 60 degrees centigrade for 9 days. So these are typical chronamperometry we obtained, and this is the results concerning the evaluation of the limiting current, against time. This measurement referred to the amperometric measurement. Simultaneously, we examine the atmosphere by the classical gas chromatographic approach. And these results here refer to the peak area of the hexanal, which could be clearly discerned from the mixture of various compounds which can be formed in the headspace. As can be seen here, as I told you before, as I said before, hexanal is one of the main products which is formed from the composition of fat products, in particular oil. So the trend for the two different kind of measurement are same. Okay, this part here until to the IT point correspond to the incubation period, which is needed before sufficient amount of products of the composition product are formed. And incredible, but amazing good, it's the agreement between the IT point obtained between amperometry and gas chromatography, which means the sensor can be a really good system, a very easy way to monitor in the real world the composition of fat products, fat products. To finish my presentation, just some results we obtained on studying silver nanoparticles. Silver nanoparticles, which are nowadays very, very much employed in several commercially available products, which vary from food, food containers, other kind of gas, good as here is simplified. But the increased amount of this silver containing product can give some problem from an environmental point of view. But why people is interested in silver nanoparticle? Because silver nanoparticles have antibacterial properties. The main reason for their for this action seems to be due to the formation to the release of silver ions, which comes from the nanoparticles, which bind to several moieties of the proteins of the cell membrane of the bacterium, which causes the death of the cell, But the formation of silver ion also by oxidation, spontaneous oxidation of metallic nanoparticles, also provide so-called reactive oxygen species, which are also dangerous for the life of the cell. Anyway, while this aspect is good for as an antibacterial properties, the amount of silver nanoparticle or silver ion which can be present in the environment and are persistent species, raise concerns in the ecosystems. So quantification or establishing the activity of this system anyway is an important aspect. So we examined, we studied several kinds of nanoparticles. These are nanoparticles commercially available. Nanoparticles are formed by silver salts by reducing processes, which by chemical reductant in the presence, for instance, of some capping agent. And these are different types of nanoparticles coupled with this PVP, PEG, and so on. More or less, they have same shape and same size. Anyway, their activity of these four types of nanoparticle is different. And we explored and detected the amount of silver ion released by using anodic stripping voltammetry. So before telling about that, I would like also to say that these nanoparticles, other than using chemical reagent, can be produced by cells, by bacteria themselves, because in the presence of silver ions or salts containing silver ions, cells can produce nanoparticles. Okay, this is the envelope of some bacteria. This is a Klebsiella oxytoca, which was studied by a colleague microbiologist here in Venice, with whom I collaborated somehow. And in the cell, you can find a lot of these nanoparticles. So these nanoparticles can release, also this nanoparticle can release silver ions. Otherwise, a silver nanoparticle can be embedded in polymers. And this, some more polymers, okay, are filled with silver nanoparticles to obtain coatings to protect food from bacteria. So in order to detect the amount of silver ion release, we can use this technique, which is called anodic stripping voltammetry. It's similar to the technique I mentioned before of the adsorptive stripping voltammetry. In this case, we reduce a silver ion on the surface of an electrode and accumulate on the surface of the electrode metallic silver that can be afterward oxidized to get this kind of peak. Okay, so the peak area or the peak height of these responses can be used to detect the amount of silver ion released. So we exploring these four different types of silver nanoparticle, we verified that the stability and reactivity in terms of releasing silver ion is much different. And this was verified by following the amount of silver ion released with time. And by the parameters we had to use to detect this amount of silver ion released. Here, after analyzing quantitatively the stripping peaks of these four products, we established this scale of reactivity, which indicated that the citrate coated silver nanoparticle has the less reactivity than the other particles, while the pig coated silver nanoparticle is more reactive. So the measurement I showed before, this measurement were performed by putting the nanoparticles in the medium. by obtaining a suspension of this nanoparticle in the medium. The medium in this case was water, but we did the same study, same investigation using food simulants. Food simulants are, for instance, for liquid foods, are, for instance, water and ethanol mixtures. So we made the same measurement in this media, and we could establish the reactivity of this system in the other media. So they almost provide similar order of reactivity. But the other aspect interesting, which we studied by voltammetry, was the use of this technique, another electrochemical technique, which is called the scanning electrochemical microscopy. I don't want to go inside too much in detail, but Mayara maybe can explain you, because she used very much this technique while she was in my laboratory. But just to tell you that the techniques involves the use of a microelectrode, which is moved on the space by a system which can provide a micrometer system or nanometer system, which can move the microelectrode at least it can approach a substrate at very, very short distances, at micrometer or even at nanometer resolution levels. So this means that we can make measurement. If we use a microelectrode and we approach a substrate very, very close to it, we can make measurement at the interface between the material and the solution. So we use this technique to establish whether silver nanoparticles embedded, for instance, in a polymeric matrices like that shown here, is composed by mainly silver not nanoparticle, I mean silver in the zero oxidation state, or it's in silver in the presence of as oxide, which means silver in the +1 oxidation state. Okay, so how we could establish this? By using proper so-called redox mediator, some reactant which can be put in the solution and can give a process at the microelectrode. When we used this system here, iridium is a chloride, which is in the oxidation state 3+. And it is oxidized at the microelectrode in the oxidation state 4+. When it diffuses towards the substrate and finds silver not particles, metallic silver in other words, it reacts because the oxidation, the redox potential of this system is much higher than that of the silver not silver plus system. So when this process happens, we have an increment of the current because a sort of catalytic process occurs between the microelectrode and the substrate. So by approaching the surface with the microelectrode, we could establish whether underneath here there is metallic silver or silver, oxidized silver. This is established by this kind of curves. Okay, so using this membrane filled with silver nanoparticles and make measurement above this surface in the close proximity, think we are almost at distance between far away from the substrate of 5-10 microns, even less if we use a properly shaped microelectrodes. Anyway, in this way, we could establish the amount of silver, metallic silver, or oxidized silver is present in each, or in not just in each, but in a given amount of nanoparticle embedded in these matrices. Okay. For instance, here, this picture here, where there are this kind of spikes, okay, it represents a line scan, so-called, which means we recorded the current developed at the microelectrode while scanning along the substrate up to about 500 microns. Where there are these spikes, it means that there are metallic silver nanoparticles. While in the zone where there are no spikes, it means that would mean that there are no nanoparticles, or if there are nanoparticles, they are not in the reduced form, but they are nanoparticles with silver in the oxidation state form. So we could, in this way, we can distinguish between which kind of nanoparticle prevail in the matrix. So this measurement, of course, can be done not only on this kind of membrane, but also, for instance, for silver nanoparticle produced by bacteria. We studied a silver nanoparticle produced by Keogh growth, which means this is a specific bacterium called Klebsiella oxytoca. But also we can perform measurement in containers used as antimicrobial, for food container used as for which prevent the contamination with the microbe, or cleaning cloth for kitchen and so on. As I said before, that the silver ions are the main motivation for providing these antibacterial properties. So silver ions, the release of silver ions at the substrate solution interface can be monitored by using the microelectrode and the approach I said before of stripping voltammetry. So instead of using the microelectrode inside the bulk solution, it can be approached to the surface and locally monitor the amount of silver ion release by performing the stripping analysis. So we did this at different solution solid substrates, like, for instance, the membrane, polymeric membrane, or food containers, and so on. And from the stripping peak, we could also establish the concentration profile between the solid substrate and solution. So in this case, for instance, the concentration of silver ion is very high in the proximity of the substrate, which is logical, of course, and the concentration decreases steeply while the microelectrode is brought far away from the substrate. This is important, it's an important result, which means this trend suggests up to which distance silver ions can act when are in contact with the medium, with the solution. Or, for instance, if there is a food packaging which is more or less closer to the food, okay, it can act differently depending on the amount of silver ion able to reach the food itself. Okay, so in other words, we can establish the concentration profiles, okay, for in a given time, or this concentration profile changes with time. So I think with these slides, it was a very long talk, but I hope I give you some information which can be useful for you, for PhD students, maybe for their research, or maybe for people, for the other students, for their work after they get the degree. Anyway, I would like to thank you for your attention, and I would like also to acknowledge the people who in the various years collaborating in this research. Some of the people mentioned here probably Mayara knows very well. Carlo Bragato, Dario Battistelli, and Antonio Tabaldo. Thank you very much for your attention.
Thank you very much, Salvatore. Very nice talk. I particularly enjoyed this last part of the use of SCCM with nanoparticles. I have a question here from Paula. She asked about, she said thank you for the lecture, and asked if you all use the SCCM to evaluate other nanoparticles like gold or anything else. Gold nanoparticles or other types.
We use it also for gold nanoparticle. In this case, not for the determination of gold ions release, because gold nanoparticles from this point of view are quite stable. Okay.
Yeah.
But you can establish with gold nanoparticles how they are distributed, for instance, in a membrane. In this way, with a different approach, it's too long to explain. In this case, how you can establish the distribution of this nanoparticle, because with gold nanoparticle, you have to exploit not the reactivity of metallic silver with the redox mediator, with iridium, for instance, but just the conductivity of the gold.
Okay, yeah.
And how assembled is this gold nanoparticle inside the membrane? Okay. In a way, you can investigate also this.
How I don't remember how small was the electrode you used in the SCCM, the radius? Because if you want to check, I'm thinking about the gold. If you want to check specifically 1 nanoparticle of gold, because I don't know what's the size of the nanoparticles either. So.
Yeah, you can also, there are some investigations. I tried, I have to confess, to use nanoelectrodes for determining the reactivity of single nanoparticles, okay?
Yeah.
The students broken all the electrodes. Each time they try to approach the substrate. It's really very difficult. The only person I know in the world who did this kind of measurement was Michael Mirkin.
Okay.
But I think the students were okay. Most of the students of Michael Mirkin are Chinese, which have a really great patience.
Yes, you have to work with nanoelectrodes.
It's not easy to work with nanoelectrodes. But actually, with silver nanoparticle, we could not just for a single silver nanoparticle, but for a few amounts of silver nanoparticles, we could establish their activity by repeating the same point, the approach curve. It's too long to explain anyway.
Okay.
But you can do similar in an easier way.
Okay. Okay, thank you. I don't know if anybody has any more questions. I don't think so. Yeah. Okay, so thank you again, Salvatore, for the excellent talk, and hope to see you soon in
somewhere
in a post-pandemic world.
Thank you, Mayara, and I hope that this pandemic situation will finish soon, and we have opportunity again to meet somewhere in the world, and maybe next time you come in Venice.
Okay.
And, but you have to come to Mestre.
Yeah, so it's quite beautiful, the building, huh? But it's not. It's quite modern, but I think being in Venice was, I don't know, beautiful.
When you were in Venice, they were still under the construction here.
Yeah.
They were, at the time, they were not ready.
Mm-hmm. Okay, thank you.
Okay. Thank you to you, and have a good evening, and
you too.
And next time.
Yes. See you.
Anyway, if someone needs to contact me eventually from
okay, you can put.
Today, some are interested in something. I didn't put my email, but Mayari can provide my email address.
Yeah.
I think I didn't put my email address here.
Put in the chat.
It's here. My email address is this one. SIG. You need a.
Yeah. IT.
Okay.
Okay, so, thank you.
I'd be happy to have your question by email.
Ok, thank you, Salvatore.
Bye-bye.
Bye-bye. Pessoal, então, obrigada pela presença em todos os seminários. A gente finaliza aqui, então, nossos 5 seminários. Espero, como disse Salvatore, espero poder vê-los em algum futuro próximo aí ao vivo. Bom? Tchau, gente.
Ok, professora, boa tarde.
Obrigada.
Tchau, professora. Muito obrigada. Tchau.
Tchau, bye-bye.
Bye-bye.